Hello, good morning. Yeah, let's start the tutorial now. Let me see. Okay, so this is the slide. Okay, so today we will talk about the solution of homework 6. Okay, so homework 6 has has 5 questions. The first one is, suppose that A star is a semi-group, and then we want to show that for any ABC in A, if this condition holds, if A times C is equal to C times A, and B times C is equal to C times B, then we will have A times B times C is equal to C times A times B. Is that okay? So how do we show? So recall that in a semi-group, the binary operator is associative. So we are going to make use of this fact to help us solve the problem. So we begin with the things on the left-hand side, A times B bracket times C. Okay. Now notice that because it is associative, so we can do the regrouping of this bracket. So A, B, C is equal to A times the bracket of B times C. And from the given assumption, we know that B times C is equal to C times B. So we can do this and then replace this one by this one. And after that, because this is a semi-group, so we can rearrange the bracket. So in that case, we can put the bracket here instead. So we have bracket of A times C times B. This is the resulting from this one. And then A times C is equal to C times A. This is from the given condition. And finally, we do the regrouping of the bracket. So in that case, we get the term on the right hand side. Now remember that we need to be very careful, okay? So we need to show the reason why each step is correct, because the semi-group operator doesn't guarantee that it is the normal multiply operator, so it may not be so it may not have the commutative property. Okay, now question 2 talks about monoid. So this time suppose that A star is a monoid, and then we let E to be its identity element. Now, for this question, we also have an extra condition. We know that for any item in A, the item multiplied by itself is always equal to the identity. And here we want to show that A star is not just a monoid, but with this extra condition, we can show that it is an abelian group. So to do so, so first of all, we see that each element has an inverse. Because an element multiply itself is equal to E. So the inverse of an element is actually itself. So every element has an inverse. So immediately we know that A star is a group. Now to show that A star is abelian, we want to show for any x and y, x times y is equal to y times x. So the critical observation, the key idea here is that we find that if you look at the item x times y, this is a single item in A. X is in A, y is in A, so x times y, this is a closed operator, so it is in A. So x times y times x times y, so this is the item multiplied with the item itself. This follows this condition. A certain item multiplied by the same item itself, it is going to be E. So this is the key observation. E, you can write it as xy, xy. Now what we are going to do next is we multiply x on the left hand side of E and y on the right hand side of E. So x times y will be equal to x times E times y. Is that okay? Because this is the E. E times anything is that thing. So xy is equal to xey. And so xey, we multiply x on the left hand side and right hand side of the right part, then we will have xx, yx, y, y. Is that okay? And now we see that x times x is equal to E, and y times y is also equal to E. So this one can be simplified to be EY xe. E identity, so it is equal to y times x. So what we have done, so we have actually shown that for any xy, we didn't assume special property about xy. We will have x times y is equal to y times x. So in that case, this operator is also commutative. So that's why A star is an abelian group. So this is question 2. Now question 3, this time we talk about groups. Okay, so suppose that G star is a group, and then it is known that the size of G is equal to P squared for some prime P. And then we want to show that given this condition, then G star will have a subgroup, let's call it G prime star, such that the size of G prime is exactly P. So once the big G has P squared as its size, then we claim that there will be always a subgroup such that this G prime is equal to P. Okay, why? Okay, so how do we do so? So we can do things like this. So first of all, let us pick any non-identity element G in big G. Yeah, because G has the size of P squared. So apart from the identity element, G must have some other element. So we can pick a non-identity element G in the big G. And then we next consider the subgroup H star generated by G. So what does that mean? So this big H contains the item G and then G squared, G3, G4, and so on and so forth until we get back to the identity element, let's say E here. So we must repeat somehow. The reason is that pigeonhole principle, we cannot have all the distinct items forever. So at certain point, something repeats, and in that case, we actually will have a subgroup. Now, Lagrange says that the size of H divides the size of big G, but by our choice, we know that the size of H cannot be 1. Yeah, if the size of H is equal to 1, that means what? That means that H is the identity element. This is the only case that we can have a subgroup of size 1. Okay, but H is not generated by the identity element, so in that case, H contains at least 2 things. And then by Lagrange, the size of H divides the size of G, because the size of G is P squared, so there are only 2 possible values of size of H. It can either be P or P squared. Now, if the size of H is P, then we're done, because we can set this H as G prime. But on the other hand, if the size of H is P squared, then we are interesting. So we are lucky that we have found out the generator of G, because this G will generate all the items in big G. So in that case, G star will be a cyclic group with G as its generator. And then we now set G prime star as a subgroup such that G prime contains the item G to the power P, G to the power 2P, G to the power 3P, and so on and so forth. So there are exactly P items inside. Yeah, G to the power P squared is actually equal to E. So in that case, we will have exactly P items inside. So we are done. So no matter which case that happens, so no matter the elements G that we found will generate only part of the group G or generate all the items in the group G, no matter which case that happens, then we can always construct a subgroup G prime star such that G prime has size P. Now, an extra question is, what happens? So here we consider the size of G is equal to P squared. Now, how about the size of G is a prime power? So for instance, it is equal to P to the power 5. Can we have a similar claim? Can we claim that when G has a prime power as its size, then G will always contain a subgroup whose size is exactly P. So I will leave this for you to try. This is correct, but then why is it correct? So I will leave it for you. Now question 4 is a Burnside theorem question. So we are given a 2x2 chessboard, And then each of the square will be colored in black or white. So we don't have any restriction about the coloring. So all the squares could be in black, all the squares could be in white. So any of the coloring of a certain square is independent of the coloring of another square. And here we want to find out how many distinct colorings are there. So what does that mean by distinct? So here we say that two colorings are the same, two colorings of the chessboard, they are the same if one can be obtained from the other by rotating the chessboard. So for instance, if we have black, white, for instance, what do we have? If we have black, black, white, black, it will be the same as if we have black, 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 white here. Is that okay? So one can be formed from the other by using rotation. So here, so this is just an exercise of Burnside. So we let S to be the set of all colorings of the chessboard. So each square, it can be colored in black or white. So there are altogether 2 to the power 4 colorings. But some of these colorings will be considered the same as the other. Okay. And then we construct a permutation group G. This is the operator of the composite function. This will be actually a permutation subgroup where each permutation corresponds to a mapping from S to S due to a series of rotations. Okay. So, so each of the item of G gives out will be a permutation of the possible colorings of S. Okay. So we will see that G has exactly 4 elements, and then they correspond to what? They correspond to the rotation by 0 degrees, which is the identity, rotation by 90 degrees, rotation by 180, and rotation by 270 degrees. Okay, so this is an exercise to test our understanding of Burnside. So once we are done here, then we can find out the number of fixed points in each of the permutation of G. So for the identity, there are 16 possible colorings of S in S, and then identity makes each one of them a fixed point after the permutation. So there are 16 of them. But when we talk about rotation by 90 degrees, then we can only have 2 fixed points. The 2 fixed points corresponds to coloring all the board in black and coloring all the board in white. So there are exactly 2. If rotation by 180, then we will see that there are going to be 4 variations. We can have the 2 diagonal in black, the one diagonal here, both squares in black or in white, and the other diagonal such that both squares are in black or in white. So there are 2 choices for the coloring for one diagonal and 2 choices for the coloring of the other diagonal. So there are altogether 4 different fixed points. And rotation by 270 degrees is the same as rotation by 90 degrees in the other way. So there are exactly 2. And using Burnside finds out the number of distinct colorings here. So it is equal to the average number of fixed points. So we add up all these numbers and divide it by 4, so we get 6 as the answer. Now we have another related question. So here in question 4b, we consider a larger chessboard, this time 4 by 4. The same consideration, each square can be colored in black or white. We want to find out how many distinct colorings are there. So we do the same definition again. This time S will be the set of all colorings of the chessboard, but this time S will be having a size of 2 to the power 16 because there are going to be 16 squares in the chessboard. So the S will be different, and similarly, the G will now be different because each of the permutation of G here will be a mapping of 2 to the power 16 colors to 2 to the power 16 colorings. So we will have a different G defined, but the number of items in G is still equal to 4. they are corresponding to the identity, rotation by 90 degrees, rotation by 180 degrees, and rotation by 270 degrees for this chessboard problem. Okay, and then the number of fixed points in each permutation can be counted by this one. So the identity is 2 to the power 16. There's no problem. Now, if we want to do the rotation by 90 degrees, we will see that each of the square in the corresponding corner of the chessboard. So the chessboard has 4 by 4. Okay, so this 4 by 4 you can have a big square. So there are 4 corners, and then a slightly rotated square, another 4 corner, and then what else? Another slightly rotated square, another corner, and the middle one. The middle one there's another square. So there are actually 4 independent squares inside a 4 by 4 chessboard. And then the coloring of the corners in these squares in each of the square has to be the same. So there are 4 squares, so there's going to be 2 to the power 4 cases for this one. So the number of fixed points when we are doing the rotation by 90 degrees, we can count it carefully. There are 2 to the power 4. And similarly, rotate by 270, there are 2 to the power 4 as well. And how about rotation by 180? So rotation by 180, we need to have the opposite corresponding points should be colored in the same way. And then we can find that the 16 squares can be partitioned into 8 pairs. So for each of the 8 pairs, we can choose a color for it. So therefore, the number of fixed points here is 2 to the power 8. And finally, for Burnside, what we can do is we want to find out the average number of fixed points. And so we add the figures here together and divide it by 4. So this is the answer. Okay. Now, finally, question 5 is a harder question for the Burnside theorem, but it's a little bit harder. Okay, we can still work out the answer easily. Okay, it just takes us some time. Okay, so here in this question, we are given a regular cube, and then we want to color each face of the cube in one of the n colors. So each face, there are n choice. And then we want to find out how many distinct colorings are there. Now this time we have a cube. So we will see that, okay, we consider that 2 colorings are the same if one can be obtained from the other by rotating the cube. So it will be a 3D rotation now. So how many distinct colorings are there? So we do the same thing as before. So we see the same slides again. So we will define S to be the set of all colorings of the cube. So we don't care whether it is distinct or not. And the set of all colorings will have how many items there? So there will be n to the power 6. Is that okay? And then here, we let G, this is the composite function. So of, okay, G and of operator. This will denote the permutation group where each permutation corresponds a mapping from a coloring of the cube to another coloring of a cube due to a series of rotation. Okay. So we want to apply Burnside, but before that, this is not that trivial, but how many elements are there in this G? Okay, so let's consider how many items are there. So one way to do so is, this is my way, so you can have your own way. So what I'm going to do is, I first try to label the faces of the cube as in a standard die. So that let's say I have a 1 here, a 2 here, a 3 here. The opposite face will be, of 3 will be 4, the opposite face of 2 will be 5, and the opposite face of 1 will be 6. So the opposite face of x in general will be 7 minus x. Is that okay? And then each of these G each of the elements of G correspond to a particular rotation of the cube. So we are going to describe a rotation by how the phases are now changed to the new way after the rotation. So what I'm going to do here is I'm going to let the original position be 1, 2, 3, 5, 4, 6. So what I'm doing the cube is like this. I have the top, describe top first, and then the front, and then rotate it. So the one by one in counterclockwise, 1, 2, 3. So the next one will be 5, and then 4, and then 6. So this is my way of describing a certain position. And so for the number of elements of G, we find that there are 24 of them. So in particular, we can have one on the top, and then you can have 2, 3, 5, 4 rotating around the for one cycle, and then the 6 at the bottom. And then if you shift it a little bit, so turn the cube just clockwise by 90 degrees, okay, horizontally clockwise by so 90 degrees, okay, then in that case we will see 1, 3, 5, 4, 2, and then 6. So I have 1, 3, 5, 4, 2, 6. So I will have all these cases. So this corresponds to the case where 1 is at the top. This is okay, so this is 2 is at the top, 3 is at the top, 4 is at the top, 5 is at the top, and 6 is at the top. So for each particular phase on the top, there are going to be 4 different variations of the final rotation. So there are altogether 6 times 4 elements in G. Now we want to find out the distinct coloring. So again, we are going to find out the number of fixed points for each rotation. Okay, so these are the values. So this is 1, 2, 3, 5, 4, 6. So the original position, recall that it is 1. So how do we count? So we see that 1 goes to 1, 2 goes to 2, 3 goes to 3, 5 goes to 5, 4 goes to 4, 6 goes to 6. So in that case, if we color the face of 1 in any of the n colors, 2 in any of the n colors, 3 in any of the n colors, 5 in any of the n colors, 4 in any of the n colors, and 6 in any of the n colors. So after this rotation, it is still a fixed point. So there are going to be n to the power 6 for this particular rotation. Now how about this? So 1, 1, so we know that we can color 1 in any way that we want. So there are n choice for the color of 1. But how about 2? We see that 2 will go to 3, 3 will go to 5, 5 will go to 4, and then 4 will go to 2. So in such a case, we must have the face of 2, 3, 5, 4 to be colored in the same color in order to have the whole thing as a fixed point. So 1 can be colored in one of the n colors, 2, 3, 5, 4 can be in one of the n colors, but these 4 of them has to be of the same color, and 6 could also be in any one of the n colors. So the number of fixed points here for this rotation will be n to the power 3. So we will have n to the power 3 here. So how about the next one? So let's have another one. So let's say, okay, so let's try this one. How about 4, 1, 5, 6, 2, 3? So 1 will go to 4, 4 will go to 2, and then 2 will go to 1. So we know that 1, 2, 4 has to be of the same color. So there are n choice for the color of these 1, 2, 4. And 3 will go to 5, 5 will go to 6, and 6 will go to 3. So we will see that 3, 5, 6 has to be colored in the same color in order for the resulting rotation to be a fixed point. So in that case, the number of fixed points will be n2, n to the power 2. So after counting the number of fixed points for each of these rotation, what we need to do is we just add them up and divide it by 24. This will be the average number of fixed points. And this is the answer for this question. Now, an interesting thing here is, if you look at this term in the first glance, it doesn't look like it must be divisible by 24. But here, we have what? We have just got a combinatorial proof, because the number of distinct colorings has to be an integer. So in that case, if everything is correct so far, then this thing no matter what n is, so as long as n is an integer, then this must be a multiple of 24. But suppose that we do not have this combinatorial proof at first. So is there a way to see that this is always divisible by 24? So I will leave it for you. So it's not that difficult. Okay, to show that it is always divisible by 24, actually, we can simplify the description a little bit. We can show that this is divisible by 3, and also we want to show that this is also divisible by 8. If if this term is divisible by 3 and 8 at the same time, then it is divisible by 24. So try your best to use your knowledge in the number theory, and then prove that it is divisible by 24. Okay, so I hope that, I really hope that my calculation is correct. And I hope you are okay with the description so far. For next week, so we will have exam 3 on Tuesday, and then I will give out the solution of exam 3 on the Thursday tutorial class. Okay, thanks all for coming, and then thanks all, and this is the end of today's tutorial. Thanks, and good luck to your exam. Okay.